Now, let's have a look at more formal methods. We have around 6 to 7 formal methods. So let's have a look at that. The first is Park test. The Park test is simply a formalization of the graphical method. So what Park suggests is, and this is directly from the Damodar Gujarati book, chapter 11. So what Park test says is that it assumes that sigma I square, that is the variance of our error term, is a function of xi, the explanatory variable xi, in this manner. So if you have such a model, you can actually do a log transformation and you'll get a linear in parameters model. Right, so you have done a double log transformation. Log of sigma I square is equal to log sigma square plus beta times log xi plus the error term vi. Okay. Now, since again ui square might not be known, in most cases the population variance of error term is not known. So Park suggests to use ui hat square as a proxy variable, as a proxy for sigma I square. So run this regression, and if you find that this beta, the estimated value of this beta, is significant, then you can take it as an indicator that there is heteroscedasticity. So the Park test is a two-stage procedure. First, you run the regular OLS regression, disregarding heteroscedasticity. Use that estimated function to calculate ui hat and ui hat square, and then run the regression to see if the beta value is significant. If it is significant, that means there is heteroscedasticity, and if it is insignificant, that means the assumption of no heteroscedasticity or the assumption of homoscedasticity is true. Now, the Park test has been criticized by Goldfeld and Quandt, saying that the regression that we are running in the second stage, in that regression, the error term vi might not satisfy all of our OLS assumptions. So it's a very valid criticism. Our second formal test that can be used to detect heteroscedasticity is the Glejser test. The Glejser test suggests regressing absolute values of ui hat on x variable which we suspect to be causing the heteroscedasticity. Okay. Now he suggests a few functional forms that can be used. So these are 1, 2, 3. There are 6 different functional forms that he suggests can be used for running the regression. And as you can see on the left hand side, that is the dependent variable in each of these case is the absolute value of ui hat. Ui hat absolute value means without the sign. So it is the modulus or absolute value. So ignoring the sign of ui hat, you can regress the suspected x variables on the absolute value of ui hat. So these are the different functional forms he suggests. But again, the Glejser test also has been criticized by Goldfeld and Quandt. One of the main criticisms that they say is that in these models, the error term vi may not have an expected value of 0. Remember, that is also one of our important assumptions, OLS assumptions, right? Standard least squares assumptions. And also that these error terms might be serially correlated and even heteroscedastic. So running an OLS regression on any one of these models might not be the smart thing to do. Okay, and as you can see, the last two models, as you can see, these are not linear in parameters. So these functional forms can actually not be estimated using the OLS procedure. You will have to use different procedures which are much more complicated. So Glejser test might not be as simple to perform for detecting heteroscedasticity. Another criticism leveled against the Glejser test is that this technique is more useful for large samples. For smaller samples, it can just be a qualitative indicator, but nothing more. So Glejser test is not as popular and accepted as the other tests. The Spearman's rank correlation test. This is the third test, formal test, that has been used to detect the presence of heteroscedasticity. You already know this formula. This is the Spearman's rank correlation coefficients formula. 1 minus 6 sigma di square divided by n into n square minus 1. Here n is the total number of observations, and di square, I hope you remember, if you are looking at two different characteristics of an individual or of two phenomenon, you rank these two characteristics, and di is the difference between the two difference between the two ranks for the same individual I or phenomenon I. So this formula and this Spearman's rank correlation test can actually be used to detect presence of heteroscedasticity. Have a look at the steps. Your first step is to fit a regression on Y and X and obtain, using your usual OLS criteria and method, obtain your residuals UI hat. Ignoring the signs of UI hat, rank UI hat as well as the suspected Xi variable. Again, a suspected Xi variable means the explanatory variable which you think is the source or is causing the heteroscedasticity in the original sample. So rank UI, absolute values of UI hat and Xi values. Calculate the correlation coefficient using your formula, and then calculate a t statistic based on this formula. Right? Since we do not have the entire population with us, we cannot calculate the population rank coefficient, which is rho s. Okay, so the samples rank correlation, I am denoting it by R subscript s. Using this RS, you can calculate a t statistic. The degrees of freedom will be n minus 2. Use the t tables and find out whether the calculated t statistic is greater than your critical value of t. If it is, we are saying that the null hypothesis is rejected. Our null hypothesis was that of homoscedasticity. So if that gets rejected, that means there is heteroscedasticity in the sample that we have in our hand or with us. Okay. Now this test can be done for more than one X variables also. If you have a multivariable model and you're not sure which explanatory variable is causing the heteroscedasticity, you can actually conduct this test separately for all the X variables. The fourth formal test for detecting heteroscedasticity is the Goldfeld-Quandt test. Once again, this is one of the more popular methods of detecting heteroscedasticity. One of the assumptions that the Goldfeld-Quandt test makes is that sigma I square, that is the variance of the error terms in the population, is positively related to one of the X variables in the model. Right? We are explaining this using a two variable model, so we have only one Xi, but if you have more than one Xi values, you might have to choose. So it is based on the assumption that the variations in the error term is positively related to the values of the X variable. Okay. So in this model, if in this model, as you can see, larger the value of xi, larger will be your sigma I square. So as a first step, what you do is you order the observations according to the values of xi. So put it in ascending order with the smallest value of xi first and going down, increasing values as you go downwards. Okay. Now what you do is you omit from the center, from the middle part of the ordered observations, you remove C observations. Okay. The value of C is either specified a priori, will be specified a priori. So you remove those C observations and you will divide the remaining observations into two equal groups. So you will have n minus C divided by 2 observations in each group. Now in both these groups, separately run the OLS regression. Obtain the residual sum of squares for both these groups. So you have RSS1 and RSS2. RSS2 is the second group, and because we have ordered the observations in as per xi values, RSS2 will have larger variance, right? Our assumption is as the xi value increases, even the variance of the error term is increasing. So RSS2 is the group which has larger variances. Okay. Now both these groups will have the residual sum of squares will have n minus C by 2 minus k degrees of freedom, where k is the number of parameters that have been estimated, total number of parameters that have been estimated. Look at this formula. Isn't it very similar to your F statistic? It is. So RSS2 divided by degrees of freedom, whole thing divided by RSS1 divided by degrees of freedom. So this is the mean of residual sum of squares, and this is also the mean of the residual sum of squares of the first group. Okay. So this value lambda, we are calling it lambda, it will follow an F distribution with these many degrees of freedom. Once again, use your F distribution table and see if the calculated value is greater than the critical value of F. If it is greater, you will have to reject the null hypothesis of homoscedasticity. That means you will have to conclude that there is heteroscedasticity in the sample given. Okay. Now, one doubt that can arise in your minds is how is the C chosen? The C is chosen based on the results of several experiments done by the same pair, econometricians Goldfeld and Quandt. They ran several Monte Carlo experiments, and they suggest from that they have come to the conclusion that if your sample size is around 30, then the suggested C value is around 8. That is, you will omit the central 8 observations and then in the remaining observations divide it into 2 groups and run 2 separate regressions for those groups. And if your sample size is around 60, they suggest that the value of C should be 16. So the number of observations to be excluded or removed from the center would be around 16 observations. Right? Again, others have suggested other C values and so on, but the C, how it is chosen and how much it is, whether it is correctly chosen, will affect the quality or the reliability of our Goldfeld and Quandt test. Now, if there are more than one X variables and a priori or prior to running the model, if you are not sure as to which X variable is causing the heteroscedasticity, you have two options. Either you can run this test on each of the x variables, or you can first run a park test or the graphical method even, and select the most appropriate x variable, and then run the Goldfeld-Quandt test. Some books also call it the GQ test, Goldfeld-Quandt test. Now let's have a look at another test, Breusch-Pagan-Godfrey test, BPG test. The BPG test avoids two limitations which were faced by the Goldfeld-Quandt test. What are the two limitations? One is that the reliability and the success of the GQ test depended on selecting appropriate value for C. And another limitation of that test was that you had to either know or correctly identify the x variable with which you are supposed to order the observations, right? So the BPG test avoids both of these limitations. So assume that you have this k variable model that you see here, beta 1 plus beta 2 x 2I plus etc. beta k x ki plus ui, right? And the BPG test assumes that the error term, the variance of the error term sigma I square, is a function of alpha 1 plus alpha 2 z 2I and so on, alpha m z mi, where these z values are one or more of the x values from the original regression model. So you can add one or more than one of the x variables, and we assume that sigma I square is a function of all those x variables. Okay, so m is the number of x variables or from the main model that we suspect to be influencing the variance sigma I square. Okay, so the logic behind the model is that we run this regression and we test the hypothesis that alpha 2 equals alpha 3 and so on is equal to 0. So if all alpha 2 to alpha m is equal to 0, what happens? Sigma I square will be equal to a constant value alpha 1, which means homoscedasticity. So the null hypothesis alpha 2 equals to alpha 3 and so on equal to alpha m equal to 0 is the same thing as saying that we have homoscedasticity. So that is the basic idea behind the BPG test. What is the procedure? Your first step, you run an OLS, obtain your residuals UI hat, then calculate sigma tilde square. Okay, the little line on top is read as tilde. Okay, this is the formula is summation ui hat square divided by n. Okay, using that, construct variable pi, which is your ui hat square divided by sigma tilde square. The sigma tilde square is actually your maximum ML estimator or your maximum likelihood estimator. The maximum likelihood estimators is a topic that I have left for the very end of the econometrics classes. Okay, so for the time being, just note that this is the maximum likelihood estimator of the population sigma square. Okay, so since we don't know the population sigma I square and the population sigma square and so on, we are making do with the estimated values. So pi is ui hat square divided by, so every ui hat square gets divided by sigma tilde square, and it is this pi that will regress on the z variables. So it's pi equals to alpha 1 plus alpha 2 z 2I and so on till alpha m z mi plus an error term vi, the residual term. Okay, run this regression obtain the explained sum of squares, and you will define a statistic which is half times the explained sum of squares. Without going into too much of statistical details, just take it for granted that this statistic asymptotically follows a chi-square distribution. Asymptotically means that as the sample size keeps increasing, as it goes towards infinity, it will follow a chi-square regression. The degrees of freedom associated will be m minus 1. M is the number of x variables that have been taken over here in this regression. Okay. So, since this statistic follows a chi-square distribution with m minus 1 degrees of freedom, look up the chi-square table at your chosen level of significance, find the critical value. If the computed test statistic, the computed value of the statistic exceeds the critical value, you will be forced to reject the null hypothesis. And like I said in the beginning, the null hypothesis is that it is a homoscedastic sample. So if you reject it, that means you have detected the presence of heteroscedasticity. Finally, we come to the White's general heteroscedasticity test. The main advantage of this test is that it does not rely on the assumption of normality of the error term. The Breusch-Pagan-Godfrey test, that is the BPG test, is sensitive to the normality assumption. It is another advantage of the White's test is that it is easier to implement as in comparison with the GQ test, the Goldfeld-Quandt test, which requires you to reorder all the observations with respect to the x variable and so on. The White's test is simpler to implement and carry out. What the White test does is, and we are explaining it with the example of a 3-variable model. So you have yi. The original regression model that you want to run is yi is equal to beta 1 plus beta 2 x2i plus beta 3 x3i plus ui. You estimate this model and you obtain the residuals ui hat. Now, taking ui hat squared as your dependent variable, regress it on alpha 1 plus alpha 2 times x2i plus alpha 3 times x3i, and then you have x2i square, x3i square, and even the cross product x2i, x3i and so on, plus an error term vi. So you are regressing the squared residuals on the original explanatory variables, their higher powers, that is squares, and even the cross product of these explanatory variables. Now, after running this auxiliary regression, this is called the auxiliary regression, obtain the R-square value of the auxiliary regression. Compute a statistic which is called n times, where n is the total number of observations, n times R-square. Okay. N times R-square again asymptotically follows a chi-square distribution. The degrees of freedom will be equal to the number of regressors in the auxiliary regression, okay, excluding the constant term, right? So the number of combinations of variables, high powered variables like x1 square, x2 square and so on, and even the cross products that you have. So the number of regressors excluding the intercept, that would be your degrees of freedom. Okay, calculate n times R square as a statistic, see if it is greater than the critical value from the chi-square distribution. If it is greater than the critical value, your null hypothesis is rejected, that is, assumption of homoscedasticity is rejected, and you have a sample where you have heteroscedasticity. and if it does not exceed the critical chi-square value, that means alpha 2 is equal to alpha 3 is equal to and so on is equal to 0. So that means your ui hat square is being determined solely by alpha 1, which is a constant, which means you have homoscedasticity. So the White's general heteroscedasticity test is a little bit more simpler to implement. But again, a few words of caution that should be shared is that when you have many regressors in the original model, if you include all those regressors, their higher powers and their cross products, you will be quickly consuming several degrees of freedom, and that could always affect the quality of your inference that you make. Another thing to be noted is that this test can be an indicator of heteroscedasticity as well as specification bias. So econometricians argue that if there are no cross products in the auxiliary regression that we run, then it is purely a test for heteroscedasticity. But if it has the original regressors, their higher powers such as x square, xi square, x2 square and so on, as well as cross products, then it is an indicator of the presence of both, or it's a test for both heteroscedasticity as well as specification bias.